Hey friends, welcome back to Miss E's Math, where we simplify college level calculus and boost your confidence with every video. Today we're diving into one of the most powerful tools in all of calculus, Taylor and Maclaurin Series. We'll break down what they are, how they work, and why they're essential for approximating functions and solving problems using common Taylor series. Let's start with a big idea. A Taylor series is a way to represent a function as an infinite sum of power terms, kind of like building a function with polynomials. Here's the general form for a Taylor series of a function f of x centered at a point C. This means each term involves a derivative of f evaluated at C, divided by a factorial, and multiplied by a power of x minus c to the nth degree. Think of it like this. We're copying the function's behavior at a point and expanding it into a polynomial that keeps getting more accurate as we add more terms. A Maclaurin series is just a special case of the Taylor series where c is equal to 0, so we're expanding around 0. The Maclaurin series looks like this. You'll obviously see Maclaurin series used for functions like e to the x, sine of the x, cosine of x, or natural log of 1 plus x, because these powers are clean and well known. Here are the guidelines for finding a Taylor series. The first step is to differentiate f of x several times. Then you're going to evaluate those derivatives at your center point. And then you're going to use the Taylor series formula that we learned on the previous slide to write out f of x. And then you're going to find a summation notation for the pattern that you recognize in the written out Taylor polynomial. Let's find the Taylor series for f of x is equal to the natural log of x centered at 1. So we're going to let f of x equal the natural log of x. So we're going to find the derivative a few times. So let's differentiate the natural log of x to get 1 over x. And we'll repeat this process a number of times so that we can see a distinct pattern going along with the derivatives. Okay, now that we have the first 5 derivatives, let's evaluate each of these derivatives at the center 1. So we're going to find f of 1, f prime of 1, f double prime of 1, etc. Now we're going to use the Taylor series formula to write out the first 5 Taylor series, first 5 terms in our Taylor polynomial. And so we're going to take f of 1 plus the f prime of 1 times x minus our center, which is 1, minus 1 over x minus 1 squared divided by 2 factorial. And we'll repeat this, adding a power to our x minus 1 and adding the power to our factorial. The most challenging thing about this is now we need to find a summation notation that represents this polynomial. So I'm going to do some rewriting. First thing I'm going to do is I'm going to expand out my 2 factorial, 3 factorial, 4 factorial, see what that means. And I'm also going to factor my coefficients of the x minus 1 term. For example, I could rewrite 6 as 3 times 2. Okay, let's simplify each term to see if we can recognize a distinct pattern that's going on. So in this third term, I can cancel out the 2 in the numerator and the denominator. And I can repeat that process on the other terms, simplifying this down to the following. So first thing I notice, I have alternating terms, so this is an alternating series. And I notice my denominators increase by 1 each time. And I don't have any coefficients, but my powers of the x minus 1 term increase by 1 each time. So I'm going to correspond this with my n equals 1, n equals 2, n equals 3. And so I'm going to write the summation from n equals 1 to infinity of, for our alternating term, we'll do negative 1 raised to the n minus 1 power. And then times that by x minus 1 to the nth power divided by n. Let's look at a few of the most commonly used Taylor series. And yes, you'll want to memorize these for your exam. For each of these commonly used series, identify the function, the Maclaurin series, and interval of convergence. Please pause the video for each of these so that you can get this information in your notes. Starting with 1 over x. And then the function 1 over 1 plus x. and the natural log of x, e to the x, sine of x, cosine of x, arctangent of x, arcsine of x, and the binomial theorem 1 plus x to the k power. We can use the common Taylor series to approximate values, evaluate limits, or even solve derivatives in integral problems. Let's look at an example. Let's find the power series for f of x equals cosine of the square root of x. So first let's recall our power series for cosine of x, which is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus dot dot dot. This pattern continues. Now I'm going to go into that polynomial and replace every x with the square root of x. Finally, let's simplify each term to get the power series for cosine of the square root of x, which would be 1 minus x over 2 factorial plus x squared over 4 factorial minus x to the 3rd over 6 factorial plus x to the 4th over 8 factorial, etc. And this series converges for all x in the domain of the cosine of the square root of x, that is, it converges for all x greater than or equal to 0. Now let's look at example 3. We're going to use the power series to approximate the integral from 0 to 1 of e to the negative x squared dx. Now this one we can't do u sub to integrate this, so instead of trying to figure out a way to integrate it, the exponential function, this transcendental function, we're going to use power series. So we're going to recall the power series for e to the x. And what this power series that we're going to approximate this integral with will have an error less than 0.01. Recall that the polynomial for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. Now in this polynomial, I'm going to replace every x with negative x squared to get Let's simplify each term in this power series to get 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial minus x to the 10th over 5 factorial. Now, we can replace e to the negative x squared power with this polynomial. So we're finding the integral from 0 to 1 of this polynomial. So that becomes the integral from 0 to 1 of 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial minus x to the 10th over 5 factorial, etc. Now let's integrate each of these terms because it's a polynomial, so we can just use the power rule for integration. And we end up with x minus x to the 3rd over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial plus x to the 9th over 9 times 4 factorial minus x to the 11th over 11 times 5 factorial. And that pattern will continue. And now let's evaluate this with from 0 to 1. So I'm going to replace every x with 1 to get 1 minus 1/3 plus, then 1 over 5 times 2 factorial just gives us 10, minus 1 over 7 times 3 factorial ends up being 42, plus 1 over 9 times 4 factorial is 216, and 1 over 11 times 5 factorial is minus 1 over 1,320, and we keep going. Now, one other thing I wanted you to do is I wanted to find the error so that is less than 0.01. Now recall earlier when we talked about our error analysis, we use our first unused term. So we need to figure out how many terms of this polynomial we need to use so we get an error that is less than 0.01. Now the best way to do that is just to evaluate each of these terms until I get a decimal value that is less than 0.01. And then that would be my first unused term, and so I would do my polynomial up to that point, not including that term. So let's start with 1 over 10, that's 0.1. Then 1 over 42 would give us 0.02, which is still larger than 0.01. So 1 over 2 to the 216 gives us 0.0046, which is less than 0.01. So that's going to be our first unused term. So we're going to do this with a power series of degree 4. And so we're approximating it with 1 minus 1/3 plus 1/10 minus 1 over 42, which we will just punch that into our calculator and see that our approximation for the integral from 0 to 1 of e raised to the negative x squared power is approximately 0.74. If I go to 2 decimal places, since I want an error less than 0.01, is rounding 2 decimal places. In today's videos, we learned that a Taylor series represents a function as an infinite sum of derivatives around its center point. A Maclaurin series is just a Taylor series centered at 0. And we've learned a number of essential lists of famous Maclaurin series for us to memorize, and that these series let us approximate complex functions with polynomials. So why do we care about Taylor and Maclaurin series? Well, not all functions are easy to work with, especially without a calculator. Polynomials, on the other hand, are easy to differentiate, integrate, and evaluate. So we use Taylor series to tell complicated functions into infinite polynomials that are easier to analyze. They're essential for things like numerical approximation, physics and engineering models, solving differential equations, computer science algorithms. I hope this video helped you connect the dots between Taylor series, Maclaurin series, and real-world math modeling. If you learned something new, give it a thumbs up and hit subscribe. Thanks for watching, and as always, stay curious, and I'll see you in the next one.